Imagine, if you will, the very earliest light in our universe, a faint, almost imperceptible echo of the Big Bang itself. What if that ancient ethereal light holds a profound secret? A swirling, subtle pattern that could reveal the astonishing details of the universe's very first moments of creation. That's the extraordinary journey we're embarking on today.
That's right. We're taking a deep dive into one of the most exciting and, let's be honest, debated discoveries in modern cosmology. We're talking about the BICEP2 experiment and its monumental search for B-mode polarization in the cosmic microwave background. This isn't just about analyzing old light, it's about potentially uncovering direct physical evidence of cosmic inflation, the universe's explosive infancy.
And as we embark on this deep dive, our goal for you is to really grasp what these elusive B-modes are, why they're so incredibly important for understanding inflation, and the almost unbelievable journey scientists took to meticulously hunt for them right down to the South Pole. We'll explore not just the discovery, but the rigorous scientific detective work involved, and what it all means for our cosmic story.
Our entire exploration today is grounded in a single seminal paper from the BICEP2 collaboration titled Detection of B-Mode Polarization at Degree Angular Scales by BICEP2. We've meticulously extracted all the important insights directly from this source, ensuring we bring you the most accurate and fascinating nuggets of knowledge.
Okay, let's start at the very beginning then, with the cosmic tapestry. When we talk about the cosmic microwave background, or CMB, for me, this is like the universe's baby photo, right?
Yeah.
A snapshot from just 380,000 years after the Big Bang.
That's a perfect analogy, yeah. The CMB is literally the faint afterglow of the Big Bang, discovered by Arno Penzias and Robert Wilson back in 1965. Its detection wasn't just a confirmation of the hot Big Bang paradigm, it fundamentally established the CMB as, well, a central tool for cosmological study. In recent years, observations of its temperature anisotropies, those tiny temperature fluctuations across this ancient light, have reached remarkable precision. These observations have truly solidified what we now call the standard cosmological model, the lambda-cold dark matter model, or ECDM.
So, CDM. What does that model tell us about how our universe works, based on this baby photo of the CMB?
Well, CDM posits a universe that is spatially flat. So it doesn't curve like a sphere or a saddle, but extends more like a flat sheet, It's also dominated by two mysterious components: cold dark matter, which doesn't interact with light, and a cosmological constant, that lambda. And that lambda is the driving force behind the universe's accelerated expansion at late times. The CMB temperature measurements have been so precise that they've constrained the key parameters of this model to sub-percent accuracy. It really is the Rosetta Stone of our universe, revealing foundational truths about its composition and structure from its earliest moments.
Okay, so we have this incredible, highly detailed baby photo of the universe. But there are some things, even that photo, as precise as it is, couldn't quite explain on its own. And that brings us to the concept of cosmic inflation. I find this just mind-boggling, the idea of the universe going through this insane growth spurt in an unimaginably tiny fraction of a second.
It is truly extraordinary. Inflationary cosmology proposes a period of nearly exponential expansion that occurred in the very early universe, less than 10 to the minus 32 seconds after the Big Bang. Think about that.
Yeah.
A billionth of a trillionth of a trillionth of a second. It's a scale that's almost impossible to wrap your head around.
So why do cosmologists believe this happened? I mean, what fundamental problems did it solve that the standard Big Bang model, even with the CMB, couldn't address?
Right. Inflation is powerful because it resolves several fundamental mysteries. For example, it explains the flatness problem, why the universe appears so spatially flat, the horizon problem, why widely separated regions of the universe, which shouldn't have been in causal contact, seem to have the same temperature. And it also resolves issues around the universe's smoothness and the absence of hypothetical magnetic monopolars. Inflation provides a natural, kind of elegant solution to all of these, offering a coherent framework for the universe's earliest moments.
And it's not just a theoretical fix, is it? Inflation also explains where the initial structures of the universe actually came from.
That's one of its most compelling aspects. Inflation fundamentally explains how the primordial perturbations we observe in the universe originated. During this rapid expansion, quantum fluctuations' tiny inherent jitters in the fabric of space-time itself were stretched to cosmic scales. They effectively became the seeds for all the large-scale structures we see today: galaxies, galaxy clusters, and those vast cosmic webs. The simplest inflationary models predict these perturbations to be highly adiabatic, Gaussian, and nearly scale invariant. And what's fascinating here is that subsequent observations have, in fact, confirmed these qualities, which provides strong, albeit indirect, support for the inflationary paradigm.
But this all sounds like physics operating at the most extreme edge of our understanding. We're talking about energies and timescales far beyond what we can test in a lab.
You're absolutely right. Inflation invokes physics at incredibly high energies, near 10 to the 16 GeV, and incredibly short timescales, less than 10 to the minus 32 seconds. This is a vast extrapolation from the regimes where our physics theories are well tested and confirmed. So finding a definitive direct test of inflation, a true smoking gun, would be of fundamental importance, genuinely pushing the boundaries of our knowledge about creation itself.
And this is where gravitational waves come into the picture.
Yeah.
Because inflation also makes a very specific prediction about them, right? This is the signal we could look for that only inflation could produce.
Precisely. One of the most compelling predictions of inflation is the generation of a primordial background of stochastic gravitational waves. These are ripples in space-time itself, produced from the quantization of the gravitational field, coupled to this exponential expansion. While these primordial gravitational waves are far too faint to be directly detected by current instruments like LIGO or Virgo, they would have imprinted a unique, subtle signature on the CMB.
Okay, so if we can't directly detect the gravitational waves themselves,
Yeah.
how would they leave a mark on the CMB that we can detect? What's the mechanism?
Well, gravitational waves induce local quadrupole anisotropies in the radiation field within the last scattering surface. That's the moment, remember, 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine, making it transparent to light. As these gravitational waves pass through, they subtly stretch and squeeze space, creating specific patterns in the light that was scattering off electrons at that time. This, in turn, causes the scattered light to become polarized. It's this specific, unique polarization pattern that we hunt for.
Okay, so we're looking for a very particular kind of polarization in the CMB. And this brings us to the crucial distinction between E modes and B modes, which is really the core of the BICEP2 discovery.
Indeed. The CMB is polarized, but its amplitude is quite small, just a few microkelvin. Most of this polarization comes in what we call E modes. Think of these like a gradient pattern, if you imagine lines of force radiating out or converging. They are generated primarily by density perturbations, sound waves, basically at the last scattering surface, and they peak at angular scales of approximately 0.2 degrees. To describe patterns on the sky, cosmologists use something called an angular multipole, or L. For E modes, this corresponds to an L of around 1,000. E modes were first detected by the DESI experiment, and numerous experiments have since refined these measurements. They're pretty well understood.
So E modes are the expected polarization from the regular processes happening in the early universe, like those sound waves propagating through the primordial plasma.
Okay.
But then there are B modes, and this is where it gets really interesting.
Exactly. B modes are the key. Unlike E modes, which have this gradient or radial pattern, B modes have a curl or swirling pattern, like little whirlpools in the polarization direction. And crucially, B mode polarization patterns cannot be generated primordially by density perturbations alone. This is the critical distinction. Their detection would be direct evidence of a different cosmic phenomenon, specifically primordial gravitational waves. The amplitude of this B-mode signal generated by inflationary gravitational waves depends directly on what we call the tensor-to-scalar ratio, or R. This ratio R is itself a function of the energy scale of inflation. So a definitive detection of B-mode polarization at large angular scales, specifically around a multipole of OL approximately 80, would provide unique confirmation of inflation and a direct probe of its energy scale. This is the holy grail.
This sounds incredibly significant. Wow. But if B modes are this unique signature, are there different ways they can be created? Because I understand there are actually two sources of B modes, only one of which is the one we're really looking for from inflation.
Sure. That's a vital point. Yeah, the universe isn't making it easy for us. While we're hunting for the primordial B modes from inflation, there's another source: lensing B modes. As CMB photons travel through the vast expanse of the universe, they get gravitationally lensed by large-scale structure things like galaxies and galaxy clusters. Their paths get bent by gravity. This lensing effect can convert a small portion of the much stronger E-mode power into B modes.
So it's like a distortion, taking an E mode pattern and twisting it into a B mode pattern, like looking through a warped piece of glass.
Precisely. That's a good way to think about it. The characteristics of these lensing B modes are that their spectrum is similar to a smoothed version of the E mode spectrum, but it's roughly 100 times lower in power, so much fainter. They also peak at similar angular scales to the E modes around LR 1000, which are sub-degree scales. The good news is that evidence for lensing B modes has already been detected by experiments like SPT and Polar Bear, confirming this gravitational effect is real, so we know it happens.
Okay, so we have lensing B modes, which are a known effect, kind of like a foreground we need to account for, but then they're the ones we're really after, the inflationary gravitational wave, or IGW B modes.
Yes, and this is where the distinct angular scale becomes incredibly important. Unlike lensing B modes, the IGW B mode signal is predicted to peak at a much larger angular scale, corresponding to a multipole LR 80. This is often referred to as the recombination bump because it relates to the physics happening at recombination. This distinct peak creates a unique opportunity to search for the primordial IGW signal because it's quite separate from the lensing effect, which peaks at much smaller scales. There's also another opportunity to search for an IGW signal at even larger scales, a less than 10, known as the reionization bump. But that requires full sky observations, which is a different challenge altogether. BICEP2 was focused on that recombination bump.
So if you find B modes peaking a Lyle around 80, that's your smoking gun.
Exactly. Because B modes at these larger angular scales cannot be generated by standard density perturbations or lensing in the same way, their detection would be a definitive smoking gun for inflationary gravitational waves. It would offer fundamental direct insights into the physics of the universe's very beginning, peering back to an epoch we've only been able to infer indirectly so far. The stakes are truly enormous.
To hunt for a signal so subtle, a ripple from the very dawn of time, you don't just need a good idea, you need an extraordinary instrument. That brings us to the BICEP2 experiment itself, a marvel of engineering purpose built for this cosmic quest, located at literally the ends of the Earth.
It really was. BICEP2 is the successor to the BICEP1 instrument, which observed from 2006 to 2008 and set an initial limit on R of less than 100.70. So it showed it was possible, but didn't see anything. BICEP2 was explicitly designed with one goal in mind, to search for a primordial B-mode polarization on degree angular scales. The principal difference and major upgrade from BICEP1 was a significant increase in detector count. BICEP2 featured a focal plane with 512 antenna-coupled transition edge sensor, or TES bolometers, operating at 150 gigahertz.
Okay, tell me about these TED bolometers. What makes them so special for this kind of measurement?
Think of them as ultra-fine thermometers, basically. They're cooled to near absolute zero, just a fraction of a degree above absolute zero, 270 millikelvin, actually. They're designed to detect the tiniest whisper of energy, the slightest temperature change from those ancient microwaves hitting them. Having 512 of them gave them an unprecedented ability to see the sky quickly and sensitively. This led to impressive, more than an order of magnitude improvement in mapping speed compared to its predecessor, BICEP1. This meant they could gather data much faster and go deeper.
And the location for this hunt was equally specialized. The South Pole. Why there? What's the advantage?
The Amundsen-Scott South Pole Station offers an almost unparalleled environment for these kinds of observations. It's incredibly dry. That extremely dry atmosphere is crucial because water vapor in the atmosphere absorbs and emits microwaves, interfering with the faint cosmic signal. It also has exceptionally low levels of other foreground contamination. Plus, you get long, stable observing periods during the polar night. BICEP2 observed the same cosmic microwave background field as BICEP1, a meticulously chosen low foreground region centered at right ascension 0 out, declination negative 57.5 degrees. This specific region was selected due to its exceptionally low contrast in dust maps, ensuring the clearest possible view of the early universe's light.
So they essentially built a giant, supercooled camera at the South Pole that sounds like a job for a very particular kind of engineer. Let's zoom in on the instrument itself and how it observed. It wasn't just the detectors, right?
Absolutely not. The whole system was designed for this. The telescope comprised a 26-centimeter aperture, an all-cold refracting optical system, so lenses, not mirrors, and everything kept incredibly cold. Light entered through a unique polypropylene foam window designed to block terrestrial interference while letting in faint cosmic signals. It then passed through filters cooled to a frigid 100 Kelvin and 40 Kelvin, and then through polyethylene lenses cooled even further to 4 Kelvin. The interior was meticulously lined with microwave absorber to prevent unwanted stray light bouncing around, and the entire telescope was located inside a large reflective ground screen to shield against signals from the ground itself. This was about creating a literally cold and dark listening post for the earliest light.
And how did they read out all that tiny data from those hundreds of super cold detectors? That sounds like a challenge in itself.
It is. The TES detectors were read out via time division superconducting quantum interference device, or SQUID multiplexing chips. SQUIDs are incredibly sensitive magnetic field detectors. This clever system allowed a single readout channel to connect to 32 detectors rapidly in succession, significantly reducing the number of wires needed, which in turn reduces the heat load going into the coldest parts, absolutely critical in such a cold environment. The sample rate for data stored to disk was 20 hertz, so 20 measurements per second per detector.
Okay, so they had this ultra-sensitive, super cold instrument. How do they actually conduct the observations from the South Pole? What was the practical strategy for collecting data day in, day out?
Right, the observation strategy was very deliberate. The receiver cryostat was mounted on a 3-axis mount capable of moving in azimuth side to side, elevation up and down, and rotating the entire telescope about its bore site, which they called the deck angle. This allowed them to precisely point the telescope and also rotate its view relative to the sky's polarization pattern, which helps disentangle instrument effects from real sky signals. The basic unit of observation was a roughly 50-minute scan set. During this period, the telescope scanned back and forth 53 times at 2.8 degrees per second in azimuth, covering a range of about 60 degrees, all at a fixed elevation. Each motion across the field, either left or right, was called a half scan.
So a continuous, precise sweeping motion across a strip of the sky. How did they build up the full map of their chosen region?
At the end of each 50-minute scan set, the elevation was stepped by 0.25 degrees, just a small nudge up or down, and the azimuth center was updated to keep tracking the right ascension 0 point as the Earth rotated. This meant the scans effectively slid with respect to the sky by about 12.5 degrees during each scan set. This constant scanning and stepping allowed them to cover the field repeatedly. BICAP operated relentlessly from early 2010 to late 2012, collecting over 17,000 of these scan sets, totaling approximately 590 days of observation time. This resulted in an effective sky area observed of 380 square degrees, reaching an impressive depth of 87 nanokelvin degrees in Stokes Q and U, those parameters used to characterize polarization. That's an incredible amount of data and sensitivity, a true fire hose of cosmic information.
Wow, 590 days of observation, 17,000 scan sets. They collected nearly 2 years of data from the South Pole. That's a staggering amount of raw information. How do you even begin to make sense of that? What's involved in transforming those raw signals into a cosmic map?
It was a monumental task, yeah. It required a highly sophisticated multi-stage processing pipeline. This pipeline was actually written in MATLAB, originally developed for an earlier experiment called QuadR, and then significantly adapted and enhanced first for BICEP1 and then even more for BICEP2. Think of it as meticulous forensic work on the data. First, they had to deal with the instrument's own response and filter out noise and glitches. This involved deconvolving the temporal response, how the detector reacts over time, and correcting for digital filtering. They also had to correct or flag rare glitches or jumps in the SQUID readout system.
And what about the atmosphere? Even at the South Pole, it must have some effect.
Absolutely. So they performed initial relative gain calibrations. At the beginning and end of each stand set, they did something called an L nod, an elevation nod. This involved moving the telescope up-down up in a sinusoidal pattern. This injects a signal proportional to the atmospheric opacity gradient into the detectors. By measuring this, they could derive a relative gain coefficient for each detector, equalize their responses, and significantly cancel out the atmospheric fluctuations. This made the data much, much cleaner. Absolute calibration came later. They also did a first round of data cuts, removing individual channels for short periods if they had issues. Impressively, over 90% of the BICEP2 data passed this initial stage, which speaks to the instrument's robustness.
Okay, so essentially cleaning up the raw signal. What came next in actually building the maps?
Once that initial cleaning was done, they moved into filtering the time stream data further. They took the sum and difference of each detector pair, remember, sum for temperature, difference for polarization. Each half scan then underwent a third-order polynomial filtering to remove slow drifts. They also subtracted a template of any scan synchronous signal by averaging across the stand set. This removed modes that might be contaminated by ground pickup or other repeating signals. And crucially, they needed to know exactly where each detector was pointing at every single moment. This pointing reconstruction was calibrated using a star camera mounted on the telescope, ensuring pinpoint accuracy to better than 0.05 degrees.
Right, and to make sure they weren't confusing temperature signals with the faint polarization they were looking for, they had to deal with potential leakage, right? How did they tackle that?
Yes, that's where the construction of deprojection templates came in. This was a critical step to mitigate temperature to polarization leakage, which happens if the two detectors in a pair don't have perfectly identical angular response patterns, like slightly different beam shapes or pointing. They essentially generated mathematical templates based on external maps of the temperature sky, like from the Planck satellite. These templates represented the leakage signal you'd expect from specific differential beam effects. They could then use these templates later in the analysis to remove that leakage component.
And then all this raw, cleaned, and corrected data stream had to be sorted and combined into actual map pixels.
That's right. They binned all the pair sum and pair difference signals into pixel grids on the sky using 0.25 degree square pixels. Data from each scan set was weighted by its inverse variance, giving more importance to cleaner, less noisy measurements. The deprojection templates were also binned in parallel. They applied known detector polarization angles and corrected for the high polarization efficiency. Then came a second round of data cuts, this time based on the quality of the L-nods and the statistical properties of the data itself, like noise stability. Some detector pairs with weird beam shapes were also cut. Overall, about 63% of the raw data was retained after all these rigorous cuts.
Still a huge amount of data, though. How did they combine everything and remove those instrumental effects using the templates?
They accumulated the pair maps over sets of 10 elevation steps, which they called a phase. Then the bin deprojection templates were regressed against the data. This process effectively found the best fit amount of each non-ideal effect, like differential gain or pointing differences present in the data for that phase. These scaled templates were then subtracted from the data, largely removing that specific imperfection. This operation also subtly filters the real signal and noise, but those effects were carefully accounted for later using simulations.
And finally, the grand summation of all this meticulously processed data led to the final maps.
Exactly. That's the final coaddition and map generation. The accumulated, cleaned, template-subtracted data from all 590 days and roughly 200 detector pairs were converted into the final temperature T and polarization Q&U maps. For Q&U, it involved a 2x2 matrix inversion for each pixel to properly combine the measurements from different detector orientations. The absolute calibration was finalized by cross-correlating their T map with existing well-calibrated maps from Planck or WMAP, resulting in a tiny 1.3% calibration uncertainty. The resulting BICEP, T, Q, and U signal maps represented the deepest CMB polarization maps ever made at degree angular scales at that time, with an impressive RMS noise level of 87 nanokelvin in nominal 1 degree pixels. They could clearly see the expected E-mode pattern, sort of vertical stripes in Q, diagonal stripes in U, but the real question was about those elusive B modes.
So they had these incredible maps. But when you're looking for something as subtle as B modes, that curl pattern, you have to be absolutely sure you're seeing it and not some accidental E mode leakage or distortion from the analysis itself. This is where the B mode purification method came in, right? It sounds like a really crucial advanced step.
It absolutely was a crucial innovation. The problem is that simple power spectrum estimation methods, things like just Fourier transforming the map, can inadvertently mix some of the much stronger E-mode signal into the B-mode signal you're trying to measure. This mixing, or E to B leakage, can arise from the specific shape of the observed sky region, the map edges, the filtering applied during processing, or even the choice of map projection. If not addressed properly, this mixing could completely mimic a B-mode signal where none truly exists, especially when the B-mode signal is expected to be so faint.
So they needed a way to mathematically untangle those distortions, essentially isolating only the pure B mode signal. How did that work?
Exactly. That's what their B-mode purification method did. It was quite sophisticated, operating in pixel space. It involved constructing these huge matrices that tracked exactly how the true signal from tiny patches on the sky mapped into the final pixels of their coded map, accounting for all the filtering and observation strategies. Using these matrices and the expected mathematical forms of E modes and B modes, they could solve a generalized eigenvalue problem, a complex linear algebra technique. This allowed them to identify a subspace within their observed map data that was guaranteed to be orthogonal to any E mode signal or any ambiguous modes that could be either E or B due to the map boundaries. They then created a purification operator to project their actual Q&U maps onto this pure B mode space.
Wow, so it's like creating a mathematical filter that only lets the pure B mode pattern through. How effective was it?
The paper states this method proved extremely effective. Their simulations showed that any residual false B modes created by this E to B leakage after purification corresponded to an R factor, that measure of the primordial signal strength, of less than 10 to the -4. Incredibly small, far below any plausible signal, and importantly, the purification didn't significantly increase the noise or sample variance for simulations that did contain real B modes. It cleaned the signal without destroying it.
Okay, that purification sounds key. And finally, how do they ensure their measurements were accurately reflecting the cosmic signal's strength, rather than being skewed by instrument noise or the effects of all this filtering?
Right. The last steps involve noise subtraction and correction for the filtering and beam effects. They followed standard procedures, like the master technique, to noise debias the power spectra. This basically involves subtracting the average power spectrum measured from simulations of noise only. Given their incredibly low noise levels, this correction was primarily relevant for the fainter B mode BB spectrum. Then, to accurately compare the observed power spectrum band powers to theoretical models, they needed to account for how their instrument beam and all the filtering steps suppress the signal at different angular scales. They calculated these effects using band power window functions, BPWFs. These functions describe the sensitivity of each measured band power to different multipoles values on the sky. The observed band powers were then divided by the integral of these BPWFs and renormalized. All these careful steps ensured that the final power spectra they presented were as close a representation of the true cosmic signal on the sky as possible.
So, with all that rigorous preparation, all that data collected at the South Pole, and that incredibly sophisticated analysis pipeline, including purification, it was time for the grand reveal. What did BICEP2 ultimately find?
Well, first, they confirmed they achieved an unprecedented level of sensitivity, producing the deepest maps of CMB polarization ever made at degree angular scales at that time. That 87 NK-RMS noise level was remarkable. But the real headline was this. When examining the BICEP2 power spectra, all the cross spectra, that's temperature E mode, TE, E mode, E mode, E mode, EE, temperature B mode, TB, and E mode, B mode, EB, were found to be consistent with the standard lens TTDM model. No surprises there. With one striking exception, the B mode autospectrum, the BB spectrum.
There was the B mode signal. What exactly did they see in that BB spectrum?
They saw a substantial excess of B mode power, particularly in the range of multipoles L between 30 and 150. And this is the precise angular scale range where the signal of inflationary gravitational waves is predicted to peak that recombination bump we discussed earlier. It was right where theory said it should be. This observed excess was truly significant. It was inconsistent with the null hypothesis, meaning inconsistent with the universe having no B modes beyond what gravitational lensing would produce at a significance greater than 5 sigma. To put that into perspective, looking at the full 9 band powers where the signal was expected, the probability of getting a result that high just by chance under the standard lens CDM model was incredibly small. 1.3 times 10 to the -7. That's equivalent to a statistical significance of 5.3 sigma. Just looking at the first 5 bands covering the peak, it was 5.2 sigma.
5 sigma. That's often considered the threshold for discovery in particle physics. How did they initially confirm this wasn't just some weird noise fluctuation they hadn't accounted for?
That's where the jackknife tests came in again. They performed a crucial temporal split jackknife test where they made maps using only the first half of the data and only the second half, and then subtracted them. If the signal was real and on the sky, it should be present in both halves and largely cancel out in the difference map. If it was due to noise or a time-varying instrumental effect, it wouldn't cancel. And indeed, this crucial temporal jackknife test did not show the BB excess in the difference spectrum. This strongly disfavored any misestimation of the noise level or some temporary instrument artifact as the cause. It strongly suggested the signal was truly on the sky and persistent over the 3 years of observation.
That's compelling. And could they actually see this B-mode pattern in the maps themselves, not just in the statistical power spectra plots?
Yes, this is quite amazing and visually intuitive. They took their Q and U maps, filtered them to isolate the range of angular scales where the excess was seen, specifically 50 old and 120, and then mathematically converted these Q and U patterns into E mode and B mode patterns on the sky. The resulting B mode map clearly showed a detection with a high signal-to-noise ratio directly in the map itself. The paper mentions a signal-to-noise greater than 2 per map mode around the peak of 70. And crucially, this detected B-mode signal appeared to be evenly distributed over the observed field. It wasn't just in one corner or following some instrumental pattern. It looked like a cosmological signal should look. The final maps visibly showed the expected, stronger E-mode-dominated pattern alongside this newly detected B-mode signal. It was like seeing a faint swirl pattern overlaid on the primary CMB structures, a visible curl in the cosmic baby picture.
Okay, a clear, statistically significant signal visible in the maps, looking like a cosmic signal and passing initial noise checks. But in science, especially with a claim this big, you don't just find something and declare victory. You then have to rigorously scrutinize every other possible explanation. How did BICP2 systematically rule out instrumental effects or systematics?
This is perhaps the most critical part of validating such a groundbreaking claim, yeah. You have to play devil's advocate against your own result. They employed a huge suite of what are called jackknife tests. Imagine you have all your data, all those observations over 3 years. You split it in half in many different ways based on time, first half or second half, based on which detectors were used, left side versus right side of the focal plane, different readout groups, based on observing conditions, scan direction, left versus right, high versus low telescope azimuths, moon up versus moon down. Then you make maps from each half and subtract them. If the observed B-mode signal was a real, persistent sky signal, it should be present in both halves and cancel out almost perfectly in the difference map, leaving only noise. If, however, the signal was an instrumental artifact related to, say, the scan direction or a specific group of detectors, it would not cancel out in that particular jackknife split. It would remain in the difference map.
And what did these numerous jackknife tests show? Did any of them fail?
Incredibly, all the B-mode BB and EB jackknives passed these tests. The paper mentions an unusually large number of these tests were performed. For instance, that temporal split jackknife for the BB spectrum had a PTE probability to exceed the observed value by chance if there's no signal of 0.992. That means it was perfectly consistent with zero signal in the difference map. This dramatic reduction in power in the jackknife spectra provided, as the paper says, empirical proof that the B-mode pattern on the sky is highly correlated between all data splits considered, strongly arguing against a systematic origin. They really covered the bases: deck angle, scan direction, time, azimuth range, moon presence, detector groupings by tile, location, multiplexer row column, even splitting by how good or bad a detector's differential pointing is measured to be. Everything canceled.
That's incredibly thorough. Beyond the jackknife tests, how did they specifically address the potential for those subtle beam systematics issues related to imperfections and how the telescope's optics pick up signals to fake a B-mode signal?
They tackled this head-on. They had performed extremely high signal-to-noise measurements of the far-field beam shape for each detector channel in situ using bright celestial sources. They could actually map out the shape of the beam for every detector. By fitting these measured beams to elliptical Gaussians, they obtained parameters describing tiny differences between detectors in apparent differential pointing, differential gain, differential beam width, differential ellipticity. The team then ran special simulations using only known temperature anisotropies as input, T-only simulations, but processed them using these measured per-channel beam shapes. This allowed them to directly estimate how much fake B-mode signal, T to B leakage, would be generated by these beam imperfections before any correction. They found that differential pointing and differential gain had the largest potential to create T to B leakage. Therefore, during the main analysis, they explicitly deprojected these modes, mathematically removed patterns associated with these effects using those templates we discussed. Differential beam width was found to be negligible, so it wasn't deprojected. Differential ellipticity was a small effect, and to avoid complex interactions with the real TE correlation on the sky, its effect was subtracted based on the beam map measurements rather than deprojected.
So after all that deprojection and subtraction based on detailed beam maps, how much potential contamination was left?
According to their simulations incorporating these steps, the residual contamination from beam effects that wasn't removed was extremely small. They estimated it would correspond to a fake art signal of only 0.001. That's orders of magnitude smaller than the signal they were seeing.
Okay, so jackknives look clean, beam systematics seem well under control. What other potential sneaky systematic errors did they consider?
They really went through the list. The paper mentions an exhaustive consideration of all possible effects that might lead to false B-modes. For instance, any effect fixed to the telescope's azimuth direction, like magnetic pickup from equipment, was effectively removed by that scan synchronous template subtraction they performed early on. They also set estimates or upper limits for contamination from things like extended beam mismatch, differences in the faint outer parts of the beams, thermal drifts in the focal plane affecting detector response, systematic miscalibration of the overall polarization angle, random miscalibrations of individual detector angles, ghost beams, unwanted responses from far-off axis directions, mismatches in the detector time constants, and electronic crosstalk between channels. All these potential systematics were found to be comparable to or smaller than that residual beam mismatch upper limit, meaning they were all individually well below the level of the observed B-mode signal. They did notice a slight excess of TB and EB power at smaller angular scales, which is consistent with a small overall rotation of the experiment's polarization angle reference. Since they knew the relative angles between detectors very accurately, they applied a small overall rotation correction, about 1 degree, to the final Q and U maps to minimize this TB-EB power. This adjustment had a negligible effect on the key BB band powers at the larger scales where the main signal was detected.
Wow, it really sounds like they turned over every possible instrumental stone. So if the signal wasn't the instrument itself, the next big hurdle is distinguishing the cosmic signal from cosmic foregrounds. These are emissions from our own galaxy or other distant sources that are physically present on the sky and could mimic the D-mode signal BICP2 is looking for.
This is indeed one of the most challenging aspects of CMB polarization measurements, and ultimately it became the central point of debate surrounding the BICEP2 result. At the microwave frequencies BICEP2 observed, 150 gigahertz, the primary foreground contaminants expected are galactic synchrotron emission, which comes from electrons spiraling in the Milky Way's magnetic field, stronger at lower frequencies, and polarized thermal dust emission from tiny interstellar dust grains aligned by the galactic magnetic field, stronger at higher frequencies. Now, the BICEP2 field was specifically selected because it was known to be an exceptionally low foreground region based on previous unpolarized dust maps. It was thought to be at least an order of magnitude cleaner than typical high-latitude areas. However, modeling these foregrounds, especially their polarization, involves extrapolating from measurements made at other frequencies, which inherently introduces uncertainties. Previous studies before BICEP2 generally predicted that foreground B-mode contamination in such clean regions should be quite small, maybe equivalent to R, less than about 0.01.
Okay, so they expected foregrounds to be small. But the biggest uncertainty in those models was the polarized dust emission, wasn't it? That's where the community had less direct data at the time.
Exactly. At the time the paper was published in early 2014, the lack of a comprehensive, publicly available map of polarized dust emission across the sky was a significant limitation and source of uncertainty in foreground modeling. BICP2 did investigate several existing models of polarized dust emission that were available, usually based on extrapolations or simulations. They looked at models like FDS, BSS, LSA, the Planck sky model, PSM, and a data-driven model, DDM1, they constructed using preliminary Planck dust intensity data. They ran simulations using these models, assuming typical parameters like dust temperature, spectral index, and crucially polarization fraction, how much of the dust emission is polarized. What they found was that the autospectra, that is, the B-mode power spectrum you'd expect from the dust signal itself, according to these models, were significantly below the level of the B-mode signal BICP2 observed. Typically, the model predictions were about 5 to 10 times smaller than the measurement. Furthermore, and very importantly, they found no significant cross-correlation between the spatial patterns predicted by these dust models and the actual B-mode patterns seen in the BICP2 maps. The predicted dust swirls didn't seem to match the observed swirls.
That sounds promising for the signal being primordial then. But there was still a lingering uncertainty about dust, wasn't there? A what-if scenario that couldn't be completely ruled out.
Yes, absolutely. And the BICP2 paper was quite upfront about this. They explicitly noted that these existing foreground models were not sufficiently constrained by external public data to exclude the possibility of dust emission bright enough to explain the entire excess signal. For example, they calculated that to explain the full BICP2 excess signal using their DDM1 dust model structure, one would need to assume a uniform dust polarization fraction across their field of about 13%. While typical estimates based on larger sky areas were closer to 5%, a value of 13% in a specific small patch wasn't considered physically impossible, just perhaps higher than expected. So this was a significant caveat. Could unexpectedly bright polarized dust be responsible?
Okay, so dust was a question mark, needing better data. What about other foregrounds, like synchrotron emission from our galaxy and extragalactic point sources? Were they easier to rule out?
Yes, those were constrained much better. To constrain galactic synchrotron, BICEP2 used data from the WMAP satellite's K-band map at 23 gigahertz, where synchrotron is brighter. They extrapolated this map to BICP2's 150 gigahertz frequency using measured spectral indices. They then cross-correlated this extrapolated synchrotron map with the BICP2 maps. Even making conservative assumptions about the extrapolation, the resulting cross-spectrum implied a contribution to the tensor-to-scalar ratio R from synchrotron of only air sync, the detagolized Nataliates 0.00008 to Nataliates 0.0041, basically negligible. This confidently showed that galactic synchrotron made a negligible contribution to the observed B-mode signal. Similarly, for extragalactic point sources, individual bright objects like distant radio galaxies, they used catalogs from Planck and polarization information from other telescopes like ATCA. Their contribution to the BB spectrum was estimated to be equivalent to IR 0.001, also a negligible amount compared to the IR 0.2 signal being claimed. So while dust remained the primary source of foreground uncertainty, the other known foregrounds were confidently ruled out as the dominant source of the BICEP2 signal.
This sounds like a strong case building for a real primordial signal, despite the dust caveat. But scientists are inherently skeptical, in a good way. They always seek independent corroboration. And BICEP2 had a powerful tool for that in its predecessor experiment, BICEP1, which looked at the same patch of sky.
Absolutely. BICEP1 observed essentially the same sky field as BICEP2, but from 2006 to 2008. And critically, while similar in purpose, BICEP1 used an entirely different focal plane technology. It used horn-fed polarization-sensitive bolometers, PSBs, with NTD germanium thermistors, not the antenna-coupled TISAs of BICEP2. This meant BICEP1 had distinct susceptibilities to different kinds of noise and systematic errors, things like microphonic pickup, magnetic fields, different shielding, different beam systematics. This makes it an excellent independent check for any technology-specific artifacts in BICEP2.
Okay, so different technologies, same sky. What did the cross-correlation between BICEP2 and BICEP1 show? Did BICEP1 see the same B-mode excess?
The results were very encouraging. Cross spectra taken between BICEP2's maps and BICEP1's maps at both 100 GHz and 150 GHz showed extremely strong correlation for E-modes. This wasn't surprising, as E-modes are bright, but it confirmed the basic mechanics of the cross-correlation process were working correctly. And, crucially, they also showed positive correlations for B-modes in the cross-spectra, despite BICEP1 having much lower signal-to-noise and not being able to detect the signal significantly on its own. Specifically, the cross-spectrum between BICEP2, 150 GHz, and BICEP1's 100 GHz map showed a detection of excess B-mode power at approximately 3 sigma significance. This wasn't as strong as the BICEP2 auto spectrum, but it was independent evidence pointing in the same direction. The compatibility between the BICEP2 auto spectrum and the BICEP2 BICEP1 cross spectra, combined with this detection of excess power in the cross spectra, provided, as the paper states, yet more evidence against a systematic origin of the nominal signal, given the significant technological differences between the two instruments.
That's really interesting. So not only did the signal seem present when observed by a different instrument, but its frequency signature, comparing the 100 GHz BICEP1 data and 150 GHz BICEP2 data, also seemed to support a cosmic origin rather than foregrounds. This is about the spectral index constraint, right? Like trying to figure out the color of the signal.
Precisely. This was another key test. To determine the frequency dependence, or spectral index, often denoted by beta, of the observed B-mode excess, BICEP2 performed a combined likelihood analysis. This considered the BICEP2 150 GHz autospectrum, the BICEP1 100 GHz autospectrum, and their cross-spectrum simultaneously. This allowed them to fit for a single common spectral index that best described how the amplitude of the excess B-mode signal changed between 100 GHz and 150 GHz. The key question was, what did this spectral index look like? If the signal was dominated by synchrotron emission, it should be much brighter at 100 GHz than 150 GHz, giving a strongly negative spectral index, under typically around -3. If it was dominated by polarized dust emission, it should be much brighter at 150 GHz than 100 GHz, giving a positive spectral index, typically around +1.5 or +2. If it was CMB, it should have a spectrum like a black body, which corresponds to beta coast 0.7 in these units over this frequency range.
And the result, what did the frequency signature, the spectral index of the excess signal, look like?
The result was compelling. The spectral index of the excess B-mode signal, after statistically subtracting the expected contribution from lensing, was found to be Baregges 9F0.7. It was consistent with the spectral index expected for the cosmic microwave background itself. This meant the frequency signature of the signal looked much more like the CMB than the known foregrounds. Quantitatively, the observed spectrum disfavored dust, assuming Bainjury plus 1.5, at a level of 1.7 sigma, and disfavored synchrotron, assuming Gannerful 3.0 at 1.6 sigma. While not extremely strong constraints individually, they both pointed away from simple foreground explanations. Furthermore, they considered scenarios that might cleverly mix dust and synchrotron foregrounds together to try and mimic a CMB-like spectral index. However, these mixed scenarios were largely ruled out by other, stronger constraints, particularly that BICEP2 Agilium map K-band cross-spectrum, which put tight limits on synchrotron. For example, a scenario trying to explain the signal with an equal mix of dust and synchrotron to give the observed effective beta would be ruled out at 13.5 sigma just by the synchrotron constraint alone.
Wow, okay. So that spectral index result really seems to weaken the foreground explanation, even the tricky mixed ones. And wasn't there even more preliminary support coming from yet another instrument that was just starting up, the Keck array?
Yes, that's right. As a final piece of corroborating evidence presented in the paper, they showed preliminary cross spectra between BICP2 and early data from the Keck array. The Keck array is essentially a successor experiment located right next to BICP2 at the South Pole, comprising multiple BICP2-like receivers. So similar technology, but an independent instrument and data set. They used data from the Keck array's 2012 and 2013 observing seasons, observing at 150 gigahertz, and cross-correlated it with the BICP2 map. This preliminary cross-spectrum also shows obvious excess BB power at low Hubers, providing additional independent confirmation of the observed B-mode signal pattern on the sky. All these layers of corroboration, internal consistency checks, cross-correlation with the ICP1, the spectral index analysis, and the preliminary Keck array cross-correlation built a very strong case for a robust detection of B-modes on degree scales.
Okay, so after all that meticulous work, ruling out systematics as best they could, finding evidence against foregrounds being the dominant source, and getting corroboration from other experiments, BICP2 concluded that the detected B-mode signal was, most likely, largely due to tensor modes, those inflationary gravitational waves. This is where they finally calculate the tensor-to-scalar ratio. What was their definitive measurement?
Based on all this evidence, the most economical interpretation of the detected B-mode signal was indeed that it was largely due to tensor modes. The theoretical template shape predicted for inflationary gravitational waves, IGW, provided an excellent fit to the observed excess BB power spectrum. Using a direct likelihood fitting method comparing their measured BB spectrum to theoretical models, lens DCDM plus tensors, BICP2 derived their primary constraint on the tensor-to-scalar ratio, R equals 0.2 low, with a 68% confidence interval uncertainty ranging from plus 0.07 down to 9 of 0.05. So R 0.0.0.05, this was the headline number.
And how significant was that finding? How strongly did it rule out a universe with no primordial gravitational waves?
It was highly statistically significant. The null hypothesis of R equals 0 was disfavored at a remarkable 7.0 sigma. The likelihood ratio comparing the best fit R.2 model to the R0 model was tiny, 2.9 by 1011. This indicated an extremely strong preference for a non-zero R. The uncertainty on their R measurement, that plus 0.07.05, was primarily driven by what's called sample variance, basically. The inherent uncertainty you get from observing only one finite patch of the sky, cosmic variance, combined with their instrument noise. This indicated they were pushing the limits of what could be learned from that specific 380 square degree observation area. Importantly, the standard lens TAPM plus tensor theoretical model with this value of R at 0.20 provided a perfectly acceptable fit to the data. For instance, the chi-squared probability to exceed, PT, for the fit to the relevant BB band powers was 0.90, meaning the model fit the data very well.
And what about the impact of potential foregrounds on this R value? Did they estimate how much R might change if some dust was present?
Yes, they addressed that. They showed that if you subtracted the B-mode power predicted by the various dust models they considered, using their default parameter values, from the BICAP data before fitting for R, the best fit R value would indeed shift downward. Generally, subtracting these nominal dust models moved the maximum likelihood R values into the range of 0.15 to 0.19, so slightly lower than 0.20, but still substantially non-zero. Critically, even after subtracting these nominal dust foregrounds, the detection of a primordial B-mode signal, i.e. ruling out R0, still remained highly significant, well above 5 sigma. The paper explicitly stated that multiple lines of evidence suggest that the contribution of foregrounds, which will lower the favored value of R, is subdominant.
This sounds like a triumph. A direct detection of inflationary gravitational waves with R.20, seemingly robust against systematics and foregrounds based on their analysis. But there was an immediate tension that arose, a conflict with other cosmological data, specifically from the CMB temperature measurements made by satellites like WMAP and Planck. It felt like one part of the universe's story was contradicting another.
That's right, and this became the crux of the intense discussion and, frankly, controversy that followed the announcement in the scientific community. The issue was this. A tensor-to-scalar ratio as large as R equal to 0.20 doesn't only produce beam-mode polarization, it also contributes to the temperature anisotropies, the TT power spectrum, of the CMB, particularly at the largest angular scales, lowest multipoles, less than 10. And RE.2 signal would imply a contribution to the temperature power spectrum at these large scales that is approximately 10% of the total power measured by experiments like WMAP and Planck.
And previous indirect limits on R for those temperature measurements, often combined with other cosmological data, were much tighter, weren't they? They seem to prefer a universe with fewer or weaker gravitational waves from inflation.
Precisely. Prior to BICEP2's direct B-mode detection, the best constraints on R came indirectly. By analyzing the detailed shape of the CMB temperature power spectrum and sometimes polarization E-modes, and combining it with other cosmological probes like measurements of the Hubble constant, baryon acoustic oscillations, BAO from galaxy surveys, and supernova data, cosmologists could constrain R within the standard BPDM model extended to include tensors. These indirect limits were much tighter. For example, the Planck satellite team, in their 2013 results combining their temperature data with WMAP polarization and other data, quoted limits as low as R less than 0.11 at 95% confidence. So BICEP2's direct measurement of R.20 appeared to be in moderately strong tension, with these indirect limits derived primarily from temperature data. It meant the universe's temperature map seemed to prefer a significantly lower R value than what BICEP2's polarization map was suggesting. This was a puzzle.
So, how might this tension be resolved? What were the potential explanations floating around? Was it simply that the dust foregrounds were much larger than BICEP2 estimated? Or did it hint at something deeper, maybe needing new physics beyond the standard model?
Oh, both possibilities were on the table. One potential resolution, and the one that gained traction later, was indeed a larger than anticipated contribution from polarized dust foregrounds to the BICEP2 signal. If a significant fraction of the measured BB power was actually dust, then the true primordial RH value would be lower, potentially bringing it into agreement with the Planck temperature constraints. However, as we discussed, BICEP2's own analysis, especially the spectral index constraints, seemed to disfavor this as the dominant explanation based on the data they had at the time. The other avenue for resolution, and one that's always exciting for theoretical physicists, involved considering extensions to the standard cosmological model. Perhaps SADM plus a simple tensor component was too simple.
Can you give us an example of such an extension? What kind of simple change to the model could potentially bridge this gap between the BICEP2 B mode result and the Planck temperature limits?
Sure, the BICEP2 paper itself offered one illustrative example. It involved allowing the initial spectrum of scalar perturbations, the seeds for structure formation, to depart slightly from a perfect power law form. They introduced a parameter called the running of the scalar spectral index, DNSDLNK, which allows the tilt of the power spectrum to change slightly with scale. In the standard AKTEM plus tensors model, this running parameter is usually assumed to be 0. However, if you allow this running parameter to vary when fitting cosmological models to the Planck temperature data, the indirect constraint on R relaxes considerably. For instance, the paper mentions that in one Planck data combination, the 95% confidence limit relaxed from R E0.11 to R.26 when running was allowed. Suddenly, BICEP2's R equals 0.2 looked much more compatible. In fact, if you added BICEP2's R constraint into these models that allowed for running, the combined data actually preferred a non-zero negative value for the running parameter. DNSDLNK equals 0.028, minimize 0.009. Now, the BICEP2 collaboration was very careful to emphasize that this example is not to endorse running as the correct explanation. It is simply to illustrate one example of a simple model extension beyond standard ACDM plus tensors, which can resolve the apparent tension. Probably there are others. It highlighted that new, precise measurements can sometimes reveal tensions that point towards potentially new physics or refinements of our existing models. It really showcased the dynamic and evolving nature of scientific understanding.
What an incredible journey we've taken today, digging deep into this landmark paper. What we've unpacked is truly a groundbreaking discovery, or at least a groundbreaking measurement. BICEP2's detection of B-mode polarization at degree-angular scales marked an absolutely unprecedented level of sensitivity in CMB measurements at that time.
Absolutely. And the team performed exhaustive, incredibly robust tests from all those internal jackknives, slicing the data every which way, to detailed beam simulations, cross-correlations with other instruments like BICEP1, and preliminary look at Keck array data, all pointing towards a real signal being present on the sky in their observations. Based on their analysis, the most compelling interpretation was that this signal was primarily from inflationary gravitational waves, yielding that tensor to scalar ratio R of 0.2, and strongly disfavoring a null detection at an incredible 7.0 sigma. And importantly, multiple lines of evidence within their own data suggested that foregrounds, while uncertain, were likely subdominant.
But as you've highlighted, This exciting finding immediately presented a new puzzle, that apparent tension with the indirect limits on our casts derived from C and B temperature measurements, primarily from Planck. This led to really profound questions about our standard cosmological model. Was the model too simple? Was the interpretation of the temperature data missing something? Or was the BICP2 signal itself contaminated more than initially thought? It hinted at the need for much more exploration.
Exactly. It spurred a huge amount of activity in the community. Was the answer a more complex understanding of foregrounds, particularly that polarized dust? Or did we need subtle adjustments to our models of the very early universe, like that running spectral index example? The scientific journey absolutely continues, and the BICP2 paper itself pointed towards the next crucial steps. They specifically mentioned upcoming data, particularly the cross-correlation with the Planck satellite's own high-frequency polarization maps, especially the 353 gigahertz channel, which is sensitive to dust, and new, deeper 100 gigahertz observations from the Keck array. These datasets would be vital in resolving the remaining uncertainties, particularly in definitively pinning down the role of polarized dust.
So, reflecting on all this, what does this BICEP2 story mean for you listening? Well, if that B-mode signal detected by BICEP2 truly was, even in part, the direct imprint of inflationary gravitational waves, then we were seeing something astounding echoes from the universe's first quantum fluctuations, potentially opening a new era of B-mode cosmology to directly probe the origins of everything. But as the subsequent analysis involving Planck would show, if these B-modes turned out to be largely explained by a more complex and brighter galactic dust foreground than previously assumed, it reveals the immense scale of the observational and analytical challenges that still lie ahead in truly isolating and seeing the very first light of creation, that faint primordial signal hidden behind the glare of our own galaxy. What stands out to you as the most intriguing possibility or the biggest lesson learned from this whole saga?